So as I already mentioned, one such a valve, by the way, a valve in Swedish is ventil. So one such a valve is actually, you can see it as a fluidic transistor. And the control channel here is then the gate of the transistor, and here I have the source, and here I have the drain. So I can cut off the source from the drain if I want to. So if I have a fluidic transistor, I can as well make a fluidic integrated circuit. And this is what we can see in the next slide. So this is a picture of a PDMS system with thousands and thousands of little valves, one next to the other. And they're all interconnected. Some are used as valves, some are used as pumps, some are used as multiplexers, some are used as a calculating unit, etc., etc. So people have made actually microfluidic computers in this way. And I'm not going to go in detail how this works, but if you have an electronics background, then you should know what a multiplexer is, and then you should understand that, well, that you can use with a few control channels, you can do a serial to parallel conversion of pneumatic signals using this transistor valves. And just like you can do the same with information in an IC, in an integrated circuit, electronic circuit, you can do the same with pneumatics. So you can actually do a very complex fluidic circuitry. And here you can see all the little colors are different dyes that are pumped in. So basically they made six very complex reactors here, and they're used for DNA processing. You can also see one of the limitations of lab on chip immediately here, because you see a very complex chip, but also I think there's about 20 or 30 different little tubes connected to the system. So just to connect all these tubes and make this leak tight and make this working, this is one of the major challenges in this kind of technology. Okay, and we're going to go more about it. This is just very cool technology. It's the main man behind this type of technology development of it is called Stephen Quake. He's a professor in Stanford, and they have a spin-off company called Fluidigm, and so maybe you can find more fluidigm.com. You should be able to find more online about this company if you want. If you're going to find information about these companies, they're going to mainly talk about their products and the end use, not so much of the cool technology that they're actually using. Right. The next type of technology platform, we're going to talk about actually 4 different types of technology platforms here for pure lab on chip. One is the PDMS base that I just showed. The second one is the lab on a CD. The third one is electrowetting on dielectric, and the fourth is droplet microfluidics. But first we go to lab on a CD. And here I'm going to talk mainly with overhead slides because it's the best way of showing things. And a lab on a CD is basically, you know, like a music CD. But instead of putting music on it, you put microfluidics on it. So you use this exactly the same format. You see this is a CD disc of 10 centimeter size. You can put it on so it can spin around. But instead of having tracks with music here, you have little channels that typically go from the inside to the outside. So if you put a little bit of liquid in the middle and then you start spinning it, it will be spun out by this is for the centrifugal force or centripetal force. It will be spun out to the side. And so you can do fluidics. So here you can see, for example, there's 96 identical copies of the same microfluidic structure. So you add a sample here and then you spin it, and you can have 96 microfluidic assays, microfluidic biochemical reactions at the same time. Yeah. So typically how you make this first is you use a clean CD, you hot emboss, you press in a microfluidic channel structure, and then you just put a tape layer on top of it and punch some holes in it, and you're basically done. Also what people do is, of course, they're going to do surface chemistry, so they're going to trap some bioreceptors typically. I'm not going to go in detail how they do that, so there's a little bit more to it, but the very fundamental fluidic structures are pretty easy to make. You can control your liquids in several ways. So first of all, if you put a droplet here and you don't do anything, you don't spin, you just put a droplet, what will happen typically is the system is hydrophilic and it's going to fill hydrophilically. So you can use hydrophilic force and hydrophobic stop valves, as we've shown previously, to stop liquid. And then you can spin to generate pressure towards the outside. You can use the Coriolis force to generate mixing behavior also. And then you're going to be able to do very integrated functions such as valving, dosing, pumping, mixing, etc., etc. And then you can do applications such as MALDI, so that's a mass spec preparation step. You can do cell studies. You can do ELISAs, which is a protein-protein protein reaction assay. And what I'm going to show here is just a little bit how the fluidics works, and then we're going to look at a video of a commercial system actually, where you see a little bit more detail. So remember now the CD that we had here. Let's go first back, and now we're going to take one of these 96 different valves here, and we're going to look at a zoom in of here. So the middle of the chip, the middle of the disc will be towards here, and the edge towards here. Yeah? So now we look at the zoom in of the system here. So we start with adding liquid to the system, and the first thing that happens is that this liquid will fill capillarily. It will run down, it will run everywhere where it can, which means it will run here and it will run here. It will stop here because I have a hydrophobic valve here. But the system will run here and it will stop here also because there's a geometrical valve. So this is after I fill the liquid, it looks something like this. The next thing that I do is that I start spinning at the soft velocity, and the velocity is soft enough so that this hydrophobic valve is not cracked, but the liquid here starts flushing. This valve is open, but not this one here. Yeah? So then it looks like this. The liquid from the top here runs away, and it will run away. This loops to the waste here at the outside, but the liquid here is retained by the valve. And now I have a very precise determined volume, in this case 60 nanoliters. So I have a very controlled liquid volume that I have sampled here. The next step is that I spin even faster, and if I spin hard enough, I get a hydrostatic pressure drop here that will be higher than the capillary valve here, and the valve will break and the liquid will flow down to this point here. This is what you see here. The liquid flows down here, and here I will have a bead bed, and I have a lot of small particles here with molecules, and here I will have a biochemical reaction. Yeah? And when that is done, I can spin even harder, and then everything is flushed out towards the outside, and it's just flushed out outside the CD, on the edge of the CD. So this is how this principle works, how such a system works. The next video